Right, this is probably going to be a short one. Quarks and Antiquarks Application of Conservation Laws, and end of test on this BAP. So we just did the particles interaction one. So quarks. Quarks are fundamental particles. Hardons, including protons and neutrons, are made out of quarks. Different combination of quarks made up different hardons. For example, up, down, strange. There are 6 quarks, but you only need to know 3 of them, obviously. So, I think I should draw the grid for this one. And you like my little strong nuclear force diagram? Of course you do. So, there is the up quark, the down quark, and the strange quark. So there should be a charge, there should be a Byron number. What else is there? And there is a strangeness. So, the charge of the up quark, 2/3. The charge of the down quark, minus a third. Charge of the strange quark, a third. Strangeness, 0, 0, 1. Byron number, I'm pretty sure is 1, a third. Ooh. And I'll tell you why this makes sense in a second. So, the anti-particles are the opposite as normal. So each quark has a corresponding anti-quark, which has the opposite properties to the quark. So quarks are fundamental particles. There are 6 of them. Fundamental means they can't be broken down anymore. So this is why it works. So a proton is a mix of 2 up quarks and a down quark. So proton is up, up, down. So as we know, a proton has a relative charge of +1 and has a Byron number of 1. So up and up. 2 of these ones. I need to do a ting. Need to do that, don't I? Yeah. Okay, sure. So it has 2 of these ones, which make it so is 4/3, and then you minus 1/3, equaling 1, which equals the first value, obviously. So that is why this makes sense. So for the next ones is antiproton, which obviously has a charge of -1, so it has the opposites. So the antiparticle of -2/3, -2/3, and then +1/3 would give -1. Next, neutron is a mix of ups and 2 downs. So an up is 2/3 and 2 downs is -2/3, which would equal 0. And anti-neutron is the exact same thing. So composed of 1 up, 2 down. So not 1 up, 2 down. So 1 up is 2/3 and 2 down is, so that is an anti-neutron. So UU is 4/3 minus a third, so that's 3/3, and because it's a knot, that is the anti-proton. 2/3 plus 2/3 is 4/3, minus 1/3 is 1, so that's the proton, and that leaves the neutron for this one. Simple. So what are the quarks that make up of a neutron and a anti-neutron? So the neutron is the up, down, down, because 1 up is 2/3 and 2 downs would give -2/3, so is that one. Simple. So quark combinations, mesons. Different combinations of quarks form different hardons. Mesons are a type of hardon containing 2 quarks, pions and kaons. Various mesons are created by up, down, and strange, and their associated antiquarks. Pions have up and down quarks and antiquarks only. Kaons have 1 strange quark or anti-strange quark. Simple. Pions are made up of up and down only. Up and down and up quarks. So it's made up of made up of up, down and up quarks. Okay, that up was confusing. So is it possible for particles to be their own particles? Yes, because obvious. Oh dear, what am I doing there? Because obviously pions, mesons are their own antiparticles. Yes, in some cases. The three different types of quarks are up, down, and strange quarks. What Byron is shown in this diagram, Byron, so that's two ups and a down, so that would be 2/3 minus a third, that would be 1, so that would be a proton. Simple. But. So, what is the strangeness of a kaon? So, the strange particle has a strangeness of -1. The anti-up has a strangeness of 0, so that gives -1 would be the strangeness. So, this table summarizes the properties of 3 quarks that you need to know about. Each one has a corresponding antiparticle. Oh dear. Antiparticle. Anti-quark. Happy? That only took like 5 minutes. Easy, 6 minutes, quarks done. So, application of conservation laws. So, how this works is basically changing quark type. Quarks can be changed via the weak nuclear force. Beta minus and beta plus decay are 2 examples of this. So, in beta plus decay, when a proton decays into a neutron, a constitute quark needs to change from UUD to UDD. So one quark changes into a down quark. Only the weak interaction can result in quarks changing types. So in beta minus decay, when a neutron decays into a proton, its constitute quark needs to change from a UDD to UUD. So it changes. So what change of quark happens in beta minus decay? So in beta minus decay, that is obviously the one where a neutron becomes a proton, so that means one of the down becomes up. Genius. So, by which fundamental force can quarks change to this type? Weak force. Weak nuclear force. So, conservation laws of physics. When solving problems in particle physics, you need to remember the following. Byron number is always conserved. Energy is always conserved, mass is always conserved, momentum is always conserved, lepton number is always conserved, charge is always conserved, and strangeness is only conserved during strong interactions. That was very underwhelming for the last one, yeah? So, conserved quantities, that is the Byron number, the lepton number, that is charge. Well, I would say mass, but it doesn't come up with it here. So, strangeness, charge, strangeness, Byron number, lepton number, momentum, and I would love to say mass here, but I know it's not it. Mass is conserved, but it's not, so it is energy. Simple. Each quark number is conserved separately. Both the muon lepton number and the electron lepton number are always conserved. Is it separately? Each quark, each lepton number. I apologize. So conserved quality, charge, lepton number. What's the other? Baryon number. Strangeness. Strangeness, charge, strangeness, momentum, and energy. I keep wanting to say mass, but that's not there. So validation of new knowledge. So this is basically when something new comes out, people have to work together to be able to validate if it's actually correct. Because if it turns out to be wrong, they've wasted a lot of time and money. Reporting new knowledge means confirming that new knowledge is correct. No, it's not correct. Reporting, validating. Yeah, not reporting. I thought it meant the likes. something else. Quarks can only change type via the weak interactions. Weak nuclear force, yep. So, blah blah blah, we don't care. Feeling, new knowledge, reporting, validating. Got it wrong last time, I apologise. So, this is now the end of topic test for this. So there's leptons and quarks, which I haven't done brilliantly on the last time I did it, which I don't know why. What kind of particle does not feel the strong nuclear force? Electron. Well, leptons. Sorry. Where do muons come from? They come from... I swear to God, this is tense. Where do the muons come from? We use the power of Google. They come from the Earth's uppermost... Oh, cosmic rays. That's where they come from, apparently. Shout at them for not telling us that we need to know this, and then giving us a question on it. What's the electron-lepton number in a muon antineutrino? That would be a plus 0. Lovely. So, in what interaction is strangeness conserved? Strong. So, what's the strangeness of a strange quark? It's -1. A little strange, yeah. How many different types of quarks are there? 6, but we only need to know 3. What of the following is not a type of quark? Muon is not a type of quark. Disappointment. What's the configuration of a proton? So a proton is 1 up, 2 ups, 1 down. 2 ups, 1 down. What type of particles are made of quarks? Barons. Barons. What type of particles? Protons. Oh, nucleons. What type of particles are made of quarks? All. What do you mean, what type of particles are made of quarks? Okay, let's find out. Google this one again. Inside protons and neutrons. What type of particles are made of nucleons? It's not neutrons. What is it? Protons. Neutrons. Mesons? Nope. What is it? Hadrons. Okay, that's acceptable, sure. What's the baron number for an antiproton? Remember that the quark composition for a proton is UUD. And the antiproton is the opposite of that. So look at the properties. The anti-up has a it has a it does have a baron number, I spelled it wrong. Yeah, add them together and that gives -1. Quick maths. Okay, what's the antiparticle from meson? Is literally itself. Yeah. What type of quark and antiquark make up pions? Up and down. Which of these statements are true? In beta minus decay, up quark turns into down quark. Beta minus is when a neutron becomes a proton, so that means one of the down becomes an up. Beta plus decay, the opposite happens, so an up becomes a down. And quarks can only change via weak nuclear. Yep, simple. So what quality is not always conserved? Strangeness. It can only be conserved in strong interactions. And we did it. Theoretically, that was a lot better than what I did last time. Peace.